Okay, so in this video, we're going to go ahead and work on solving a buffer problem. So first, let's read through the problem. We'll go through what a buffer is, how we set things up, how we want to think about things conceptually and quantitatively, and then work through a solution. So first off, you'll remember a buffer is a base and its conjugate acid or an acid and its conjugate base, both in a solution in non-zero quantities. More specifically, in quantities with in amounts that are at least one order of magnitude away from one another, right? Or if you would prefer, plus or minus a pH unit. As we're going to see here, the ratio of the base to conjugate acid or acid to conjugate base is what's going to determine the pH of that buffer solution. Furthermore, because of the way a buffer solution works, since the acid in a buffer solution neutralizes any added base, and the base in a buffer solution neutralizes any added acid, as a consequence of these, if the conjugate acid in the solution neutralizes added base, not only does it neutralize that added base to zero, right? So the added OH minus just goes away. But for every molecule of OH minus that gets neutralized by conjugate acid, a molecule of conjugate acid, that converts that molecule of conjugate acid into its conjugate base form. So all we're really doing if we add OH minus or H3O plus to a buffer solution is we're just changing the ratio of the conjugate acid to the conjugate base, right? If we add a base, we're consuming conjugate acid and forming conjugate base. If we add an acid like H3O plus, we are consuming conjugate base and turning it into conjugate acid. And that ratio and the equilibrium thereof of that conjugate acid base pair is what determines the pH. And here soon we'll also look at a shorthand way of calculating this. So first off, let's identify things here. So we're going to start by calculating the pH of a buffer solution consisting of 0.50 moles per liter of HClO. That's hypochloric acid, I believe. So that is our acid, HClO, aqueous, plus, now note this is an equilibrium, right? So water is going to act as the base in this case. And we've got an equilibrium here. And so the HClO becomes its conjugate base form, ClO minus. And then, of course, that H2O becomes H3O plus aqueous, right? So there is our acid-base equilibrium. Now, what makes this a buffer, as we're going to see here, is that we have non-zero concentrations of both the conjugate acid and the conjugate base. So for part A here, we're just going to calculate the pH of this solution, right? So currently we are solving for part A. So we're going to do an ICE table as you learn in chapter 18. So you could think of it as we're just doing an ICE table for the pH of an HClO solution. But the main difference is going to be rather than having 0 moles per liter of the conjugate base, ClO minus, we have a non-zero amount, all right? So let's plug in our values. So concentration here is 0.50 moles per liter, shown right here. Okay, water, of course, we ignore. ClO minus, well, each equivalent of that dissolves forms one equivalent, 1 mole of Na plus and 1 mole of ClO minus. So really, that 0.60 moles per liter of sodium hypochlorite is just 0.60 moles per liter of hypochlorite, the ion, because the sodium doesn't matter. We can ignore it. So 0.60. And then our H3O plus, we're going to assume initially that there's none of this. But remember, so assume 0, but reality is this would start at 1 times 10 to the negative 7th moles per liter, because that's the natural quantity of H3O plus in pure water. But to make our math easier, we will make the assumption that it's 0, and it'll make our ICE table so much easier to solve, right? So we're going to calculate Q here. So products to the powers of their coefficients over reactants. And so note, we get as expected, and this is part of the reason we assume that the concentration of H3O plus or OH minus, if we were doing that type of buffer, is 0. We kind of ignore the contribution to the amount of H3O plus or OH minus from pure water. So that's 0. So that means Q is less than K, which we can already see there. Ka equals 2.9 times 10 to the negative 8th. And so that means minus on the reactant side, plus on the product side, and these are all 1 to 1, so it's minus X plus X plus X. So it would end up with 0.50 minus X, 0.60 plus X, and then X as our concentrations. Now our Ka right here is 2.9 times 10 to the negative 8th, and that is equal to this current setup, 0.60 plus X times X all over 0.50 minus X. Now we could just solve this using a quadratic, but let's do our test. So we take our smallest non-zero initial concentration, which is 0.50, and we divide by our K value, which is 2.9 times 10 to the negative 8th. And we're asking, is it greater than 400? So let me bring up my calculator here. So we have 0.5 divided by 2.9 exponent negative 8. And we get a very, very, very large number, 1.7 times 10 to the, let's see, 1, 2, 3, 4, 5, 6, 7. 7th, 1.7 times 10 to the negative 7th. So yes, it's greater than 400. So we can ignore additions or subtractions of X. So now our problem becomes 2.9 times 10 to the negative 8th equals 0.60 times X over 0.50. Because what this assumption allows us to do is just ignore any additions or subtractions of X. Remember, the assumption is that X is so small that adding X or subtracting X from the initial concentrations will not significantly change those concentrations. In other words, the equilibrium concentrations of those values are very similar to the initial concentration of those values, right? So now if we solve for X, right? So X, which is equal to the H3O plus concentration at equilibrium, is going to be 2.9 exponent negative 8 times 0.5 divided by 0.6, and we get 2.4. Let's see here, we've got 2 sig figs, 2.4 times 10 to the negative 8 moles per liter. If we take the negative log of that, note 2 sig figs means 2 decimal places in the pH, and so we get a pH of 7.62. So I got here. So let's look back at everything here. So we have 0.5 of that, 0.6 of that, 2.9 exponent negative 8. Yeah, that's correct. Yep, that's correct. So 7.62 is the pH of that solution. So just above 7, okay? So now that we've done that, let's see what happens if we add acid or we add base, okay? So now let's look at part B. So we're going to take that same solution and we're going to add 0.020 moles of NaOH, which is to say we're just adding 0.020 moles of OH minus. Because again, the sodium's not going to do anything, okay? And as you're going to see here in a moment, we will need to know our volume of our solution, okay? So here's the thing. If we add OH minus, we need to look at which of our two species is going to react with OH minus in our buffer, okay? And we could see here if we add OH minus, it's going to react with our conjugate acid in the buffer, meaning it's going to hack. Here, I need to move everything here real quick. Give me one moment. Okay, there we go. Meaning, when we add that OH minus, it's going to react with our conjugate acid and single arrow, right? Because of the OH minus, because OH minus is such a strong base, the strongest base in water, this is a single arrow to the right. And so the OH minus gets converted to just H2O, and the HClO becomes ClO minus. So we neutralize our OH minus, forming H2O, and our HClO gets converted to the conjugate base form. So for this, we're going to do an ICF stoichiometry problem. So to do that, let me adjust some things here. Move this over, move this back over here. We need to know our moles of each of these things in the reaction, okay? Because this is stoich. We're going to pretend that the moment we add the OH minus, it's going to do stoichiometry first, right? So this is part B, B1 we'll call it, okay? We're going to do stoichiometry first, and then we will do the equilibrium problem, okay? It's just to make our math easier. In reality, the reaction's happening and the equilibrium is constantly shifting until it reaches the new established equilibrium. But mathematically, let's pretend the moment we add that OH minus, this reaction is going to happen first, and then whatever's left over at the end will then equilibrate to form a buffer with a particular pH. So we know we added 0.020 moles of this, okay? We added 0.020 moles of that. For our conjugate acid, we will need to calculate that because our initial concentration of the conjugate acid is 0.50 moles per 1 liter, and we're told that the solution has a volume of 1 liter. So that means, let me do this math up here. So this is moles of HClO. So we have our 1 liter, because that's the volume of solution we're told we have. And we have 0.50 molar solution. And so that means we have 0.50 moles of HClO. Okay. And then for our ClO minus, same math. We have a 1 liter solution. However, the concentration of this, if you'll remember, is right here, right? So there's the acid concentration, the initial acid concentration, and here we have the initial base concentration. So, there should have been 1 there, okay? So 0.60 moles per 1 liter, and so that leaves us with 0.60 moles of ClO minus, okay? So that means that this value goes right here, and this value goes right here. Okay, so let's plug those values in there real quick. So our 1 liter solution contains 0.50 moles of HClO and 0.60 moles of ClO minus. So now with this stoichiometric type table, it's always going to be minus limiting reactant, plus limiting reactant. And so looking at these two things, since this is a 1-to-1 reaction, we should be able to quickly see here that this is the limiting reactant and this is the excess reagent, right? So if we subtract the amount of limiting reactant from both reactants, that means this is automatically going to be 0, meaning all of the added OH minus gets consumed by the HClO. the amount of HClO in moles is going to go down by the amount of OH minus that it consumed. So 0.050, 0.50 minus 0.020 leaves us with 0.48 moles of acid left over at the end. So 0.48 moles. And then for our hypochlorite ion, it's going to be 0.60 plus 0.020 because for every mole of HClO that reacts with OH minus, we create 1 mole of ClO minus. So it will go up. So 0.62 moles. Okay. And so here are our new mole amounts that we need to then use to calculate the new concentration. And so the new concentration is going to be equal to the new volume of the solution, which is still 1 liter, divided by our new mole amount, which is 0.48. So we get 0.48 moles per liter. And then for this guy over here, our new, I shouldn't write it in there, but new concentration is 0.62 moles divided by our new volume. And so 0.62 moles per liter. Okay. Now, in reality, normally, this will be added as a volume and a concentration. And so just remember, for future problems, the new volume is always going to be the volume of the buffer solution plus the volume of whatever you added. And that is what should go on the bottom here when you're calculating your new concentrations. In this case, we said we added OH minus without changing the volume. So that means the volume of the buffer is 1 liter and the volume added is 0 liters, and thus the new volume is also 1 liter. Okay, so now that we've done that, go back up here. Let me grab this. Okay, and so now, instead of those old values in this problem, we're going to replace them with the new values, right? So here we have 0.48 moles per liter. That's the new concentration, right? And then here we've got the new concentration. And that is now 0.62 moles per liter. So 0.62, 0.48. Now the rest of the problem works the same. If we do the test again, it's gonna succeed again. So I'm just gonna shortcut this. 2.9 times 10. Is it 2.9 or is it 2.7? It is, yeah, 2.9 times 10 to the negative 8th. 10 to the negative 8th equals, and so the test is going to work that plus and minus x can be ignored. 0.48. And so again, x, which is the H3O plus concentration, is going to be based on these concentrations because, as I said, adding OH minus or H3O plus to a buffer, all it really does is cause the concentration of the conjugate pair to shift, the ratio to shift, and that's what's happened here. Our 0.50 concentration for HClO went down to 0.48, and our ClO minus that started at 0.60 went up to 0.62. And so 2.9 exponent negative 8 times 0.48 divided by 0.62, and we get 2.2 times 10 to the negative 8 moles per liter, which is a pH of negative log of that 7.65 is the new pH. Our old pH was 7.62. So we can see, right, that our buffer did change a little bit, but just a little bit. So note, we added OH minus, and then the pH, the new pH is 7.65. So you'll note it did become more basic, but not directly because of the added OH minus. It instead changed because the amounts shifted by that amount of OH between the conjugate acid and conjugate base. Now, effectively, you would do all the same work that we just did here, only the main difference is going to be, since we are adding H3O plus, well, what reacts with H3O plus? Well, that's going to be the conjugate base. So we get a different reaction, still a single arrow because H3O plus is such a strong acid. And so we would form, again, H2O because we're neutralizing that H3O plus, and we would reform, we would convert some of that ClO minus back into HClO. And so this works exactly the same way as we did before. Oops, ICF, because this is a stoich problem. And if we read the problem here, so this is, so that was B1. This will be B2 down here. So now we'll do C1 and C2. Okay, so we'll call this part C1. And then down here, when we get there, we'll have C2. So this one's a little bit different. It's the same deal as we had before, okay? So we calculated, so we have a 1 liter solution. Let me move this around here, just making some room. So here, remember, we have an old concentration. So an old concentration of this of 0.50 moles per liter. And so we have a 1 liter solution, which means we have 0.50 moles of that to start off with. Okay, here again, our old concentration is 0.60. That's from the original problem. And that converts, since it's a 1 liter solution, to 0.60 moles. Now, here's a new added step, right? We added, if we look here, 30 mils of a 1.5 molar HCl solution. Now, again, when we see HCl, what do we really mean? H3O plus, because strong acids 100% convert to the strongest acid that can exist in water due to something called the leveling effect. So HCl becomes H3O plus. Another strong acid, HNO3, it just becomes H3O plus. So we take our 30 mils, we convert that from mils to liters. So we divide by 1,000, and then we have our 1.5 moles for every 1 liter of this solution. And so if we do that math, 30 mils divided by 1,000 times 1.5. And so you get 0.045 moles of this have been added. So 0.045. Let's double check that. So 30 mils divided by 1,000 is 0.030 times 1.5, because that's the initial concentration of that solution. Oh, I've already screwed up. Let's back up here. Remember how I told you these were a 1 liter solution? You got to read carefully here. So for this part of the problem, it said imagine we have a 0.5 liter solution rather than a 1 liter solution. Okay, so 0.5 liters and 0.5 liters. So doing that math, correcting this, we have 0.5 liters times a 0.5 moles per 1 liter. And so we get a molar concentration of 0.25 moles in a half liter of solution. And over here, 0.6 times 0.5, we should get 0.30. Yes, we do, 0.30 moles. Okay. So 0.030 liters. All right, so now we have our problem again. Remember, since this is stoich, stoichiometry we're doing here, not an equilibrium problem, see the single arrow? Stoich. We're dealing in moles, and in the change row, it's changing by the limiting reactant. So again here, we can see that this guy is the limiting reactant, meaning this guy is in excess. And so when we subtract that, this drops to 0 because the limiting reactant, it's a limiting reactant, it goes away first. Now we subtract that limiting reactant amount, 0.045, from our initial amount of ClO minus, because that's going to react. And so we get 0.25, oops, I want to do that in blue. 0.255 moles of that guy. No, it'll be 2 decimal places, okay? And then over here, we're going to do the same thing, only instead of removing by the amount of limiting reactant, we're adding, so it's 0.25 plus 0.045. And so we get 0.295 moles. Okay, now to get our new concentrations of each of these, we need to know our new volume. Well, our volume of the buffer solution is 0.5 liters, and we added 0.030 liters. So that means our new volume is 0.53 liters. So if we take our mole values here of 0.255 and our 0.295, and we divide by our new volume, because remember, we mixed a solution into another solution. So, and in doing so, if we calculate our new concentrations, so we would need to convert all of the stuff we mixed together into moles first, and then to get the new concentrations, we would have to add the volumes of each solution together that we mixed and divide our new mole values by our new volumes to get our new concentrations. So 0.255 divided by 0.53, our new concentration of this is 0.48 moles per liter, and our new concentration over here, 0.295 divided by 0.53, is 0.56 moles per liter. I rounded early. Technically, you wouldn't round just yet. Okay, and so now we are again going to do just an ice problem. Okay, so we're going to do an ice problem again. Same exact problem. We're not switching to from a Ka to a Kb problem. We're just going to treat it like a Ka problem, because technically it doesn't matter. Okay, so again, we're going to make all the same assumptions that we did before, only now we've got these new concentrations. So 0.56 moles per liter, so 0.56 minus x, and then over here, 0.48 moles per liter, and 0.48. Okay? All right. So again, K, 2.9 times 10 to the negative 8th. You can do the test again, but again, we're going to know that x is insignificant, so we can approximate this by ignoring any addition or subtraction of x, so we don't deal with the quadratic, 0.56. Okay, and so again, if we solve for x is going to be the H3O plus concentration. And so 2.9 exponent negative 8 times 0.56 divided by 0.48. should give you 3.4 times 10 to the negative 8 moles per liter. And so if we take the negative log of that, the pH, negative log, because we're dealing with H3O plus, is 7.47. No units. Okay, and again, note 2 sig figs, and thus we have 2 decimal places in our answer. Okay, so again, note, by adding H3O plus, we did shift the pH to a more acidic pH, right? Because 7.47 is lower than 7.62. However, it changed less than a pH unit. Okay. Now that only works because the stoichiometry held. If at any time you add enough base or acid to convert all of either the conjugate acid or conjugate base in the buffer, it just blows the buffer apart. It won't stop the pH from drastically changing at that point. Okay. Now, there is something we could do instead, and I just want to show it to you real quick. It's called the Henderson-Hasselbalch equation. Okay. And so it makes an assumption. Assume your initial concentrations of conjugate acid and conjugate base are equal to your final concentrations of conjugate acid and conjugate base. In other words, plus or minus X can be ignored. If that's true, we can take the Ka expression here. So note it was Ka, and we're going to make this, well, we're going to make this specific. So the Ka expression here would be the Cl, the concentration of ClO minus, which is our conjugate base, times our H3O plus concentration, all over HClO, which is our conjugate acid. And if we rearrange this, and run a negative log through it, we get the following master equation. The pH of a buffer equals the pKa plus log of the conjugate base, the equilibrium conjugate base concentration over the equilibrium conjugate acid concentration. And voila, we have the Henderson-Hasselbalch equation. So how does this work? Well, first off, let's do these two problems again with our added acid and our added base, right? We would still need to do this top part on both sides. We would still need to do that part, okay? What this replaces is the ice table. So this replaces the ice table. But again, you must test X. X must be insignificant for this equation to work, okay? So note, if we calculate the pH over on the right side, right, if the pK, actually, at any point during this, we can calculate the pH. So our initial solution, right, so the part A would be pH equals, and then our pKa is negative log of 2.9 exponent negative 8. So that's going to be 7.54. So that's our, that is our pKa, and then log of our conjugate base concentration is in part A, it is 0.60, and our acid is 0.50. Okay, and so that means this part ends up being log of 0.6 divided by 0.5. And so that ends up being 0.079. And so if we do that math, 7.54 plus that answer, we get 7.62 for our initial pH of the buffer. And if we look here, 7.62. That's what we got in the first part of the problem. Now, if we go over here and we do part B, okay, same problem, pH equals 7.54 plus log, again, of conjugate base over conjugate acid. But now, again, we're going to skip the ice table. So here's our conjugate base and here's our conjugate acid. We still need to do that stoichiometry step. We still need to see how the ratio of concentrations has changed before we plug it into the Henderson-Hasselbalch equation. So now instead of 0.6 over 0.5, we have 0.62 over 0.48. So 0.62 over 0.48. We do that math. We take the log of 0.62 divided by 0.48, and we get 0.11 and so on. So we take 7.54 plus that answer. We get the pH after adding base is 7.65. And indeed, again, that is what we got, 7.65. Okay, so added OH minus. So let's do one more. Let's do part C using the Henderson-Hasselbalch. Added H3O plus. Okay, so same deal. pH equals, and then our pKa is 7.54 plus log of, and again, conjugate base over conjugate acid. So we go to our stoich step. What was our base? 0.48. What was our acid? 0.56. Okay, so 0.48 divided by 0.56. 0.48 divided by 0.56. I think I might have done something wrong there for that. I think I got things switched around. No. 0.5, 0.25. No, I think it's okay. Well, anyway, let's continue. Okay, so 0.48 over 0.56. So the log of 0.48 divided by 0.56 is negative 0.067. And so 7.54 plus that answer, which is negative, is 7.47. And again, that is the pH we got there. Okay, so this Henderson-Hasselbalch equation is a shortcut to skip doing an ice table as long as x is not significant, as long as we don't have to use a quadratic to solve for what x is, and thus in this case, the H3O plus concentration. That concludes solving this problem.